Okay, now we are gonna look at this transformation exercise. So first they are asking us to find the AB component of the voltage. So we've seen before the alpha beta component is given by the Clarke transformation, and here we have the matrix. Okay. So we just multiply each voltage by this matrix. So we have 300 cos 100 pi t plus 10 cos 100 pi t. We have for b's 300 cos 100 pi t minus 2 pi over 3 plus 10 cos 100 pi t plus 2 pi over 3, and we have 300 cos 100 pi t plus 2 pi over 3 plus 10 cos 100 pi t minus 2 pi over 3. Okay, so we need to do these calculations to get the alpha beta components. Now this can be done with trigonometric identities, but I just went the easy route and used MATLAB to simplify. So here are the results. It's gonna be 465 cos 100 pi t and 435 cos sine 100 pi t. So these are our components, and the way I did it, I just plugged. I had the transformation matrix, I multiplied it by the voltage matrix here in the code. Let me see if it can be shown easily. Okay, so if you see here, this is just the transformation matrix, and this is just the voltage matrix. And using simplify, MATLAB give us the simplified result of this multiplication, and that's our alpha beta. And similarly, we are gonna do something with the DQ components. So we have here the DQ. So for DQ, the transformation matrix is cos of the angle. In this case, they are telling us there is 100 pi of, yes, then we have here sine of the angle minus sine of the angle and cos 100 pi t. Then we multiply this by what we just found here. Actually, let me just grab this, because this is what we're multiplying by. And again, You can do all the math, but just with MATLAB, I plug the transformation. I had the matrix transformation matrix and multiply it by the alpha beta, simplify it, and MATLAB gives me the result here. So now we have that our alpha beta is just of the Q answer, or the Q, rotating reference frame. It's 15 cos and 200 pi t plus 450. And here we have minus 15 sine 200 pi t. Okay, so that's what we transform from the three voltages to the dq component. It's just applying the transformations. Now we have this example. It is asking us to find the power expression in alpha beta component and then do it in dq component. Okay, so just as a reminder, we know that the reverse Clarke transformation when we have our phasors ABC is equal to 2/3 of 1 minus 1 minus 1/2 minus 1 0 square root 3 over 2 minus square root 3 over 2 multiply. So this is our transformation matrix, and here we will have our alpha beta phasors. So if we apply this to the example that they are giving us here, then we can say that 2/3. Now we are gonna transpose this to have it just as they have it uh, in the exercise. Here they have it like this. Okay, and I'm gonna write it better as voltage phasors. So this is the component, this is the beta component, and then we multiply by the transpose matrix. We have to transpose, so the multiplications are still valid. And we do the same 2/3 for the current but for the current we don't have to transpose the matrix because we have it like this in the example. So this will be just times our alpha and beta components. So now we can multiply the scalars. So we have here 4th, 9th, and we're gonna have still our alpha beta components of the voltage. Okay, and then we multiply these two matrices. The way you multiply matrices is just multiplying the rows times the columns. So this is, you just do each one and it's gonna give you 3 halves for when you multiply this row. So this one times this one plus this one times this one plus this one times this one. Okay, just a reminder of matrix multiplication. So when we do it, we're gonna have this result, and here we're gonna still have our alpha and beta components of our current. Okay, now if we look at this looks a lot, this matrix looks a lot like an identity, so we can just factor out the 3 halves. So, and when we multiply it by our scalar, we are gonna have here, remember we're calculating power, so we're gonna have 2 thirds, 3 halves times 4 ninths is 2 thirds. We have our component of alpha and beta, and this is gonna turn this matrix into, when we factor it out, well, I'm just gonna write it. It's gonna turn this matrix into our identity, and it has the dimension so that we can multiply it with this one. And when you multiply with the identity, it's just gonna give you the same result. So power is gonna be 2 thirds of the alpha beta components of the voltage times the current alpha beta of the alpha beta components of the current. Okay, so this is our power expression for alpha beta. They are asking us to do the same for dq. Okay, so we are gonna do exactly the same that we did before. So we have our thirds, but instead of having alpha beta, we are gonna express it in dq. So we have to multiply by our transformation matrices. So this is the same, just that we apply it for the Park's transformation. So this is the transformation matrix for the Q component, and this is the transformation matrix for the Q components of the current. So sine 5 cos 5, and they are transposed because the matrices are in a transposed form. Okay. And now when we do this multiplication of these two matrices, we are gonna get that it is just an identity matrix again, which is pretty convenient. We're gonna have 0, 1, 0, 1. You can do all the math, but it's just gonna give you the identity, and then you can use MATLAB or do the math manually. And again, if we multiply this by our matrix, it's just gonna give us our same matrix. So we have that the power in the Q component is just our 2 thirds of our voltage components times our current components. And that's it.